Good morning. All right. So I am going to give the second lecture, my second lecture now. And as I understand it, these lectures are appearing online someplace, actually photocopies or images of these pages. So I'm going to do my very best to make this legible. So to begin with the beginning, this is lecture 2, and this is going to be called Basic Facts. Great. All right, so I'm just going to get started. So at the end of the last lecture, I defined for you the hyperbolic Laplacian and the notion of a harmonic Maass form. So that's where I want to start. So the hyperbolic Laplacian is a differential operator which is defined for every real number k. So if k is a real number, delta k was defined to be this differential operator. And just to remind you, z throughout is in the upper half of the complex plane, with real and imaginary parts, x and y. So what we're interested in is we're going to be interested in these non-holomorphic modular functions, which are harmonic. And I'm going to be a little bit more precise today with the definition. So the definition I'm about to give, you'll see very quickly, excludes the Eisenstein series E2 star from consideration. That's going to be important for us. So here's a definition. A function m, a real analytic function, say m from h to c is a weight k. I usually talk much faster than this, but when you have to synchronize your speed with your hands, I now realize I probably talk very fast. So my hand can't speed up. All right, so real analytic function will be m from h to c is a weight k harmonic Maass form. On, say, a congruent subgroup, say gamma, if the following holds. I'm going to lie a little bit about most of these parts, but for those working in the student groups, this will be made precise. It'll be a weight k harmonic Maass form if it's modular. So m of az plus b over cz plus d is equal to, I'll put quotes there because in the half integral weight case that's not quite right, cz plus d to the k times m of z for all a, b, c, d in gamma. The function is harmonic, namely it's annihilated by the Laplacian operator. And 3, this is what I didn't talk about yesterday, and it's going to be very important for a lot of the things that we do today. I need to know that there are principal parts at all cusps. So for the cusp at infinity, this will be described as follows, namely that there is a polynomial. Let's call it, I don't know, a piece of m of q inverse, such that the form m minus pm of z, so I'm already committing an abuse of notation. Q is throughout e to the 2 pi I z. So when I'm thinking of p of m of z, I'm thinking of the Q series. So m of z minus pm of z is big O of e to the minus epsilon y. Oh gosh. Ooh, epsilon y for some positive epsilon as y goes to infinity. What does this mean? This is what we're going to refer to as the existence of a principal part at the cusp infinity. So I've run out of room on this page, but I can say it. We're going to demand that there are principal parts of the Fourier expansions for every cusp. So for example, the Haupt module on SL2Z, say J minus 744, would have principal part Q inverse. So just let me give you as an example. as an example, the classical J function, I'm going to subtract 744. It will be my habit because I may later talk about cusp forms that have poles, with the idea of extending Eichler-Shimura theory to the space of harmonic Maass forms, where the critical feature will be that the Fourier coefficient at the constant term is 0. This series starts out as q to the minus 1 plus 196, I think it's 884, plus some gigantic numbers. And in this case, the principal part of J minus 744 is the polynomial Q inverse. So it's going to be very important for us that we can establish the existence of principal parts, which could be trivial, but we do need to have principal parts at each cusp. So one note, E2 star is not a harmonic Maass form in this sense. All right. So if you remember, the correction term doesn't have this bounded exponential decay as you approach infinity. All right. So the important thing to note, and this is what we will be spending most of our time talking about, are the properties of the Fourier coefficients of these harmonic Maass forms. So let me begin by writing the word Fourier expansion. I'm going to discover quickly that I'm going to probably not write everything that I say. All right, so for simplicity, I want to suppose throughout that k is a half integer, includes the integers, and I'm doing this only for, I forgot the k part. Okay, so k is a half integer. It's going to be at least one, and I'm just going to say that for reasons that will be clear in terms of the examples I want to describe, this will be very convenient. And it turns out that there's one special function that we need. It's the incomplete gamma function. An incomplete gamma function is basically the gamma function where you've just forgotten to integrate, where you would customarily begin to integrate. So gamma of alpha of x is the integral from x to infinity, e to the minus t to the alpha minus 1 dt. Okay, and this is a very, very important special function. In a moment, I'll give you an integral formula for this special function, one which is central to the theory of periods for elliptic curves. So if you've done actual numerical calculations for computing periods of elliptic curves, you've probably implemented maybe some algorithms involving the incomplete gamma function. So in fact, one of the quickest ways of computing central critical values of modular L functions is to just decorate the Fourier coefficients of a function like delta with a sequence of values of the incomplete gamma function. So the main lemma here arises from standard separation of variables argument is as follows. So what am I going to suppose? Let's suppose that f is a harmonic Maass form of weight 2 minus k on some congruent subgroup gamma, where the translation matrix 1, 1, 0, 1 is in gamma, again for simplicity. Okay. Then what is true, then the following is true, then at infinity, at the cusp infinity, f has an expansion of the form f equals the sum over n greater than negative infinity, which means that there are potentially a finite number of terms with negative n, that's what that means, of cf plus of n times q to the n, and then plus the sum n less than 0, c minus f of n times the incomplete gamma function evaluated at the arguments k minus 1 times 4 pi the absolute value of n y q to the n. And the Fourier coefficients will be these two sequences of numbers. The cf plus of n and the cf minus of n are the Fourier coefficients. So one feature that these harmonic Maass forms share with the Eisenstein series E2 star is that the Fourier expansions of these functions want to be little more than Q series. in terms of the Eisenstein series E2 star, you had to decorate with the reciprocal of the imaginary part of Z. And when you do have principal parts, that correction is replaced by this decoration involving the incomplete gamma function. And right here is where you see the mild non-holomorphicity of these functions f. So remember here that this y is the imaginary part of z. So Fourier expansion is very mildly non-holomorphic. So what we really like about, all right, and of course, as Fourier coefficients, these are complex numbers. So if you want to see a proof, if you want to do the proof, I think this is exercise number 1 in the problem sheet. So it's the starting point for most of the theorems that we're going to be talking about today. So in view of this lemma, we have some natural terminology. So throughout, I'm going to suppose that f is a weight 2 minus k harmonic Maass form on gamma. Again, k is at least 1. Gamma is a congruent subgroup containing the translation matrix. And if f is such one of these functions, you can see the function splits into 2 parts. And we will call one of these parts f plus. We'll call one of these other parts f minus. So f plus will be the sum on n of c f plus of n q to the n. This is what we'll refer to as the holomorphic part, for obvious reasons. And the f minus, well, what else could we call it? The non-holomorphic part. So again, just copying from that lemma over there, that will be the sum on n negative, cf minus of n. Now all this gamma stuff, gamma k minus 1, 4 pi absolute ny, q to the n. And we will refer to this as the non-holomorphic part of f. So the natural question that you'd want to ask, is, what is the significance? What is the significance? What's the significance of the Fourier coefficients c f plus of n and of the coefficients cf minus of n? What's the significance of these two seemingly independent sequences of numbers? It's a great question, and it turns out there are many answers to this question depending on the actual relationship these harmonic Maass forms have with classical modular forms. There's no single answer to that. So the first question that we have to ask before we're in a situation where we can answer this question in a case-by-case, on a case-by-case basis, would be to ask, how are these spaces? How are spaces like h of 2 minus k of gamma related to classical modular forms? And just to be completely explicit, by classical modular form, I'm going to refer to a meromorphic modular form, some function which maybe has poles, but that's the only thing that would keep it from being what you would call a holomorphic modular form. All right. So there are many answers to that question, and just to maybe get started very, very slowly would be to start with an easy, here's a word, easy answer. And the easiest answer I can offer you to the question, how are these spaces of weight 2 minus k harmonic Maass forms related to classical modular forms, is by just set theoretic inclusion. h2 minus k of gamma contains properly the classical weight 2 minus k weakly holomorphic modular forms. So that exclamation point, the bang, refers to weakly holomorphic modular forms. And a form is weakly holomorphic. That just means that if there are poles, they're allowed, but must be supported at cusps. If you're lucky, well, and why is this an easy answer? All you have to do is check that every weakly holomorphic modular form is annihilated by the Laplacian operator. It's pretty straightforward. That's an exercise, I guess, exercise 2 for Amanda. Another easy answer number 2, is that the non-holomorphic part of a harmonic Maass form certainly does not uniquely determine the form. So in other words, if you have F1 and F2 harmonic Maass forms of weight 2 minus k, which have the property that, of course, F1 of minus, the non-holomorphic part of F1, if it equals the non-holomorphic part of F2, then certainly F1 minus F2 will equal the difference of their holomorphic parts, because the non-holomorphic parts cancel. And of course, that's going to be a weakly holomorphic modular form of weight 2 minus k. And of course, you can add a weakly holomorphic modular form of weight k to a harmonic Maass form of weight k, and just get a different harmonic Maass form of weight k. Basically the converse of this easy answer. So I have to offer you a better answer, and this is where the subject really starts. And the better answer, the deeper answer about how these harmonic Maass forms are related to classical modular forms comes from understanding the action of a certain differential operator. So there's a very nice operator xi. If you're familiar with Maass raising and lowering operators, feel free to do the translation into that language, but I'm going to call this the xi operator throughout. There's a very nice differential operator xi, which annihilates holomorphic functions, which preserves modularity. So this is for any real number w. Xi is 2I times y to the w times, well, basically d dz bar bar. And as an exercise, it's not difficult to check that xi w of f is a harmonic Maass form, is the same as, of course, xi w of f minus, because this contains a d dz bar. And, well, that's really good. What we want, however, is a statement about how harmonic Maass forms are related to classical modular forms. So the lemma that really has content is this. So suppose that F is a harmonic Maass form of weight 2k on a congruent subgroup gamma. And this is where the principal parts come into play. Then you have that the image of this xi operator for weight 2 minus k, evaluated at F, is actually a cusp form of weight k on that same group gamma. Great. There's much more to this lemma, several parts. Moreover, we have the following two facts. We have that, well, as above, xi 2 minus k of f is xi 2 minus k of f minus, because it annihilates a holomorphic function. And we have a closed formula for this. It's negative of 4 pi to the k minus 1 times the sum on n, c f minus of negative n to the k minus 1 q to the n. So if you're given a harmonic Maass form of weight 2 minus k, and you have the Fourier coefficients for its non-holomorphic part f minus, now it's a plus, f minus, you have explicitly for you the coefficients of a cusp form. So right here is an exact, simple map that maps harmonic Maass forms to cusp forms of weight k. The most important feature is that, and xi 2 minus, xi 2 minus k, not only does it map h2 minus k to sk, it does so surjectively. This is a surjective map. There are no cusp forms of weight k that escape being an image of this map. All right. So the natural question that we have to ask is something like this. Given say, a cusp form capital F, say, capital F, how do we do all of the following? how do we find, so if that's a capital F, how do we find a lower f in h2 minus k of gamma such that xi2 minus k of f is big F? How do we find a preimage under this differential operator? And of course, finding this preimage has infinitely many answers. This question has infinitely many answers because adding a modular form to a harmonic Maass form gives you another harmonic Maass form. So not only do you find this F, how do you find a good F? So again, this harmonic Maass form F is a sum of two functions. I did it again. Everybody knows how to do that. It's called reciprocation, but that's not what I mean. How do I find, oh, I almost did it again. All right, so how do you find a good F? And the point is, how do you find the holomorphic function, a holomorphic function, a candidate for a holomorphic function, which when added to this F minus, which can be computed by means of this formula, that magically gives you a harmonic Maass form. And let me be completely precise. Let me give you a setting for which we might want to do this calculation. So here is a completely explicit setting, an explicit example, using, again, the number 37. I like that. I didn't know you're 37, so we're going to make that the theme of the day. So I don't remember I do remember being 37. So let E be this elliptic curve over Q with conductor 37 from yesterday. I don't remember the defining equation, but let E be this elliptic curve. So what do we know by the modularity of elliptic curves? There is a cusp form we could call Fe, weight 2, it's a new form, on gamma 37. That follows by, by the modularity of elliptic curves. We like that. And a natural question you could ask is, with this F, so I'm going to put this F right here, it's a cusp form of weight 2 on gamma 037. With this F, I'd like to ask or find a preimage. I'd like to find a preimage of this function F with respect to the operator, with respect to this differential operator xi. Okay. So that corresponds to finding F minus plus an F plus. But this is not the only question regarding lifting maps for modular forms that would be of interest corresponding to this elliptic curve of conductor 37. So if you're familiar with the Shimura correspondence, we know that there is going to be a corresponding, in fact, a family of these half integral weight modular forms, say GE, of weight 3 halves on the congruent subgroup gamma 0, I think is 4 times 37. I'm going to put an asterisk by the Shimura correspondence because it turns out that the Fourier coefficients of this function G are really, really important. So what I want to say in this star is that by work of Waltz-Bourget, and others, we know that the coefficients, it's known that the coefficients of G interpolate the values of the quadratic twist of the L functions associated to E, so let's call them something like LED of 1. The coefficients of this cusp form of weight 3 halves interpolate these numbers LED of 1 as D varies over fundamental discriminants. And of course, these numbers are very important in testing, say, the Burton-Swinnerton-Dyer conjecture. Theorems of Coley-Vaughan will allow you to determine whether a particular quadratic twist of this elliptic curve has rank 0 or not just basically by examining the Fourier expansion in G and asking whether a number you're looking at looks like 0 or doesn't look like 0. It's that easy. I like that. But the theme of the day is the surjectivity of this differential operator xi. So there are also harmonic Maass forms of half integer weight. So although we may be interested in the pullback of the xi, and I'll talk about the pullback of that xi, for example, for the delta function in a moment, that's a more interesting case. What we might be interested in is the pullback under xi of this function ge. And this pullback will tell you that there will be some good function, let's call it capital GE, which is a GE. I'm going to write this very slowly so I don't turn minus into minus 1. I did it right. Plus GE plus, where this harmonic Maass form will have weight 1/2. It will be on gamma 0 4 times 37, and its image under the xi operator will just be this G. The natural question is, how do you find a good F? And it turns out that you can find a good F, which in this case was a good G, rather. And finding this good G, thankfully I called this G for good. The question you could ask is, what did we learn? What do we learn about these quadratic twists ED by merely finding this GE plus? Just the mere surjectivity of this differential operator together with the modularity of elliptic curves tells you that there's a power series, actually infinitely many of them, but there will be a good one, a minimal one, whose identity, when you've determined it, tells you something about E's that you didn't already know. I could tell you the theorem right now. I think many of you can probably guess the theorem right now based on what I said yesterday, but what I'd like to do is give a completely down-to-earth example of a calculation like this, where the cusp form of weight 2 for this elliptic curve is replaced by, say, the delta function. All right, so let's do that. So it turns out that what I've described is a classical type of problem, and it's called the theory of periods for modular forms. Periods for modular forms appear many places. Of course, they're important for constructing elliptic curves from modular forms, which was briefly discussed in the earlier lecture. This is the so-called easy direction for modularity. And what we want to do is we want to turn this structure of this F minus and this F plus into a device where we have a good understanding of both the analytic and the arithmetic interpretation of the coefficients of the gadgets we're defining. So the fact that I want to sketch out now is the following. So suppose that little f is a weight 2 minus k harmonic Maass form on a congruent subgroup gamma, and suppose that its paired cusp form image, xi of 2 minus k of f, is some form, say, capital F of weight k. Okay, and what is the fact? Then we have, well, we want to study F plus, but let's first understand F minus. We then have that F minus is the period integral as a function, a non-holomorphic function in z bar. This is the period integral of capital F. So I'm going to turn those quotes into a precise statement. So there's a very precise way of thinking about the pullback of this differential operator xi. And when I speak of these period integrals, this is really somehow making a little bit more modern the theory that Eichler developed years ago when you're talking about like Eichler integrals of classical cusp forms. And also when speaking of what are called period polynomials, which have been studied extensively by, well, Eichler, Shimura, Manin, and others. So to make this precise, thankfully, requires just one identity for a special function. And the identity for the special function is that I never get it right, so I literally copy I times 2 pi n to the 1 minus k of the incomplete gamma function, gamma of k minus 1, 4 pi ny q to the minus n. So now I've inverted n here as positive. This is equal to the integral from negative z bar to infinity, I infinity, of e to the 2 pi I n tau divided by negative I times tau plus z to the 2 minus k power d tau. The incomplete gamma function is a gadget that you can recognize as formally integrating from negative z bar to I infinity q to the n. Therefore, because of the existence of the Fourier expansion, what f minus is clear. So, as a special case of Hecke eigenforms, let me tell you what we're really computing here. So, in the special case of level 1, let's suppose that this cusp form capital F has level 1. So suppose that F is of level 1 is a Hecke eigenform, normalized Hecke eigenform. Okay, let me just remind you what the periods are of this function. Then the periods of F are then for the integers n between 0 and k minus 2. The numbers L f of n plus 1, these are the critical values for the L function for f, and they can be formally computed as follows. So it's 2 pi to the n plus 1 over n factorial times integral from 0 to infinity f of I t to the n dt. These are the periods of f. In view of the fact that the incomplete gamma function in this special case is just the period integral of the exponential function q to the n, by assembling over the Fourier expansion of your Hecke eigenform f, what you get is this easy is a word theorem. So suppose then that, say, k is at least 12, is an even integer, and suppose that capital F, and suppose that little f is a weight 2 minus k harmonic Maass form with the property that xi 2 minus k of f is a normalized Hecke eigenform capital F. Then what's true? Let's define a function p. Let's define a function capital P depending on big F and little f of z by the following. So define capital P f of little f of z. Define it to be 4 pi to the k minus 1 divided by gamma of k minus 1 times this difference, f plus of z minus f plus of negative 1 over z to the k minus 2. Define pf of z to be this multiple of this difference of f plus. If f, what is f plus? F plus is, again, the holomorphic part of f, and as I've said, the non-holomorphic part of f is this period integral of the delta function. So what this term capital P is the obstruction to modularity for the holomorphic part of this harmonic Maass form. Given that the non-holomorphic part is non-zero, namely it's a period integral of like delta, we know that this is a function which is not trivial. So what is it? Then we have, and it's basically just an elementary formal identity, we then have that P f of z bar, so I'm actually stating this in greater generality, is a polynomial. It's a sum over the same integers n, the critical values in this critical strip, sum over n, L of f, f. This is a big F, L of big F of n plus 1, divided by k minus 2 minus n factorial, times 2 pi I z to the k minus 2 minus n. It's a complex polynomial. It's not a hard theorem, very elementary theorem. It's just using the formula for periods that I wrote down a moment ago. So this is an easy theorem, but this theorem has been used as, how to say, the prototype of learning how to think about all of these harmonic Maass forms in some level of generality. So what I want you to think of when you see this easy theorem, to paraphrase, the easy theorem says that in integral weight, and this is the case of SL2Z, the obstruction to modularity, I now realize how impatient the person I am. I'm watching the words get spelled out so slowly and I'm frustrated with myself. In integral weight, the obstruction to modularity, i.e. P f of f, is just the classical period polynomials of Eichler. In other words, it's the generating function for these critical values. So, the question is, how is this easy theorem generalized when, for example, k is not even an integer, when k is a half integer? What does it mean to measure the obstruction to modularity? In that case, there's no such thing as a half integral weight period polynomial. There's no such thing as a half integral weight period polynomial. All right. So before I move on, what do I want to say? I guess I want to work out an example. Hesitate a little bit to write down numbers, but I think it's really important to see one example. An example that if you wanted to, you could reproduce on your own if you knew how to program. So the example I want to consider, it's almost like a law. You have to start with the delta function. So let's let f be the classical Ramanujan delta function, which is, of course, this, well, the only normalized cusp form of level 1 in weight 12, delta. So what do we know? We know, as I said, we know that the xi operator, which in this case starts at weight minus 10, maps surjectively the space of harmonic Maass forms of weight minus 10 onto S12. And what I'd like to do is just say in words, by the method of Poincare series without, and let me not go into that any further. I'll talk about that a little bit more later. By the method of Poincare series, there is a best choice for F. So what is F? F is going to be the harmonic Maass form of weight minus 10, which is F minus plus F plus, which is going to map directly to delta. And let's let F be this best choice. What turns out to be true for this best choice, it turns out that the Fourier expansion of F plus, or 1 over 11 factorial times F plus, is equal to q to the minus 1 minus 65,520 divided by 691. So already all of you who understand the important role that 691 plays for the delta function will realize that some of the same tricks will work right here for F plus. But minus 1,842.894, I don't know, q. Let me just say that this is this number right here, I'm going to call CF plus of 1. It's the first coefficient of the holomorphic part, the coefficient of q to the 1. I'll say more about that in a moment. Minus 23,274.07, whatever q squared. It turns out that the holomorphic part of this best choice, holomorphic part of this best choice for F is this, and, well, what is it? It is really very ugly. doesn't take my poor handwriting to make it ugly. It doesn't matter how good your handwriting is. It wouldn't restore this F plus to beauty. Okay. So a question you might ask is, why is this best? Why am I saying that this F plus is a best choice? Why is it a best choice? And in particular, how do we see delta from F plus? Surely I don't see the coefficients of the delta function among these awful looking numbers. How do I make that connection? All right, so this is how you can fix this. This is a principle of renormalization. So let's renormalize. What I'd like to do is I'd like to renormalize F plus as follows. I'm actually going to kill the 11 factorial here so I'm going to define F plus hat of Z to be this holomorphic part of F, this thing that I said is really quite ugly. And what I want to do from that is I want to then subtract CF plus of 1. This is, what is that number? The 1842 point, who knows what, 89, whatever. But then, because I know that this is somehow related to the theory of Eichler integrals, I'm going to subtract from it summation tau of n to the minus 11, and get this Q series. F hat plus of Z equals 11 factorial times, this is the holomorphic part of the harmonic Maass form, and this is what comes from the period integral of delta. This is the kind of thing that we expect to be there. And then what do you find? You find that, well, F hat plus of Z still looks messy. It looks messy for a number of reasons. You probably don't have numbers n to the minus 11th power memorized in your head. So at first glance, if you do these calculations the wrong way, it will look like these coefficients are just crazy decimal expansions, crazy real numbers. Turns out that that's not true. So we renormalize yet again to get an F hat plus of Z, which is just going to be Q ddq to the 11th power. Just have faith, because we were trying to kill those denominators of F hat plus of Z. And what you get turns out to have integer coefficients. This number, 1842.89, is probably transcendental. And let me say, if you prove this number is transcendental, you prove Lamar's conjecture that the tau function never vanishes. More on that in a moment. But this F plus of Z turns out to be a function many of you who are working with Frank would be able to compute with. So as an exercise, and what is the exercise? The exercise is that this F plus hat of Z that has integer coefficients show that if P is an ordinary prime for delta, then the limit, I'm going to state it kind of a lowbrow way, the limit as n goes to infinity of this F hat. In fact, this is not exactly right. There's a slight correction factor I have to make, which I won't make. But it turns out F hat plus hit with the U operator at P to the N divided by C hat plus P to the N, just to ultimately obtain a Q expansion whose first leading coefficient at Q is 1. This is delta. So as n goes to infinity, these coefficients that have exponential growth converge to delta monotonically as a power of P. Okay. So I'd like to make some remarks. What I wanted to say first is, what is it that the holomorphic parts of these harmonic Maass forms are revealing? In the case of integer way cusp forms, it's another way of thinking about what we call period polynomials. If you're interested in studying the critical values of these period polynomials, they're obtained by measuring the obstruction to modularity. And the holomorphic parts of these harmonic Maass forms, their obstruction are these polynomials. So we don't really need to talk about that anymore. If you're interested in arithmetic properties of the Fourier coefficients of classical cusp forms, the following turns out to be true. So here's some remarks. I believe that CF plus of 1 is transcendental. And it can be shown in this case, should be, so I'm going to put this in quotes. In this case, it should be possible, I'm pretty sure I know how to do it, maybe I've even written it down before. In this case, if CF plus 1 is transcendental, if you can show that, then you've shown Lamar's conjecture. So I'm not asking anyone to think about this problem because a set of numbers that you can prove are transcendental is kind of paltry. I'd be very surprised if you could do that. All right. But what do we know? We know the following sort of thing. We know that if capital F is, say, a weight K cusp form on gamma 0 n, such that F has Cm, then we know that the corresponding best harmonic Maass form little f of weight 2 minus k on gamma 0 n. So I'm dropping all reference to Nevin-Tippis characters, of course. We know that the best choice for a harmonic Maass form of weight 2 minus k that maps to f, such that xi 2 minus k of little f is f, has the property that the Fourier coefficients of the holomorphic part, CF plus of n, are algebraic integers. And they're basically in the ring of definition of the coefficients of little f together with the values of the Nevin-Tippis character. So I wanted to give you a concrete example of this differential operator that somehow reveals that the non-holomorphic parts and the holomorphic parts of Fourier expansions of harmonic Maass forms are already interesting numbers. And what we will do next time, I guess is about time for me to stop. What I'm going to do next time is to leave the space of these classical modular forms, and I'm going to talk about traces of singular moduli. I'm going to talk about Borchard's products. And I'm going to talk about derivative formulas, L prime ED of 1 and LED of 1, depending on whether D has a positive or negative sign of the functional equation for elliptic curves E over Q by making use of the surjectivity of xi 2 minus k. This is a wonderful operator. Surjects onto any space of cusp forms you ever want to calculate. So if you take a pullback of a cusp form you wish to study, we just discussed the case of delta, define what you want to be your best choice, and then depending on the properties of the cusp form or modular form you've started with, you've probably revealed something you didn't know and wanted to know something about. Great, that's all I wanted to say today. Thank you very much.